This lecture is about separation of variable for PDEs. I will illustrate separation of variable using these two examples. So in those two examples, I am not considering any initial condition or boundary condition. I will just find a family of general solution. Okay, so for the first problem A, let's rewrite this. Du dt equals 1/4 d square u dx square. And let's first recall from first order differential equation, if I had du dt equals lambda u, then I could use separation of variable very easily. Du over u equals lambda t, or ln of u is lambda dt, sorry, ln of u is lambda t plus a constant, and that we know u equals some constant c times e to the power lambda t. Okay, so that's the separation of variable for ODE. For PDE, we can think the same way, because on the right hand side I have 1/4 second derivative of u with respect to space. So that is a differential, linear differential operator, and it has eigenvalues. So I can think of it is very much like on the right hand side lambda times u. If I knew the eigenvalue, I don't know the eigenvalue. Assume that the eigenvalues are lambda. So assuming lambda is an eigenvalue, I can write the solution u xt is some constant, and this time the constant will depend on space or special coordinate x. So I will denote this constant by sx e to the power lambda t. So that is the first step I get. U is sx times e to the power lambda t. And by looking at this quantity, I can see that if lambda is a positive number, then the solution will grow continuously and it will blow up. So that tells me that lambda has to be a negative number. Lambda will be a negative number. And this form can equivalently be written as sx times h of t, with h of t is e to the power lambda t. Okay, so what we do next? We take this trial solution, plug into the equation, and see what happens. So you differentiate with respect to t, you get lambda times s e to the power lambda t. On the right hand side, 1/4, differentiate twice with respect to x, you get s double prime e to the power lambda t. Okay, maybe since e to the power lambda t is not 0, you can take it out from both sides, and then you get an eigenvalue problem. S double prime equals 4 lambda s. S double prime equals 4 lambda s. Okay, so then it has a characteristic root plus or minus I times 2 square root of lambda. and we know that this equation has solution, sines and cosines. So solution could be either s equal to cosine 2 square root of lambda or times x, obviously, sine square root of lambda 2 square root of lambda times x. Then the solution will be e equals e to the power lambda t cos 2 square root of lambda x or e to the power lambda t sine 2 square root of lambda x. So we have two different solutions of a linear partial differential equation, and by principle of superposition we will write the general solution uxt some constant a times e to the power lambda t cos 2 square root of lambda x plus p times e to the power lambda t sine 2 square root of lambda x. Okay, so let's come back to the second example. So let's first bring the second example here. Which is du dt du dx. So this is a first order homogeneous linear differential equation. This one does not have the coefficients constant. But still we can find the solution. Even if you think of that the right hand side has an eigenvalue, and if the right hand side can be written as something like, say, x over t lambda times u. So still if you want to solve that, it is not just e to the power lambda t, but it is still separable. We can solve this. And obviously that is one option. But now I just want to be a little more formal. I want to take the solution based on my previous example. So it's s of x times, and this time, since I know this is not e to the power lambda t but something very similar, so I'm going to write it h of t. Now I'm going to plug this back into the PDE. So on the left hand side will be s times h prime, and on the right hand side x over t s prime times h. So s is a function of x, h is a function of t. So I take all the x's to the left hand side and all the t's to the right hand side. And also if I do that, if I bring s prime from the right hand side to the left hand side, I get s over s prime, which is not convenient in terms of differential equation. So I will just switch the order, take s to the right hand side and then write it to the left hand side, and obviously x should be here, and then I take h to the left hand side and take it to the right hand side. Okay, so t times h prime divided by h. So since I have x times s prime by s on the left hand side and right hand side everything is t, left hand side everything is s, so I can write it equal to lambda or equal to minus lambda. I'm going to write minus lambda just from some experience, it doesn't matter. So if so, then I have two sub problems. So one problem, if I look at from the left hand side, I get x times s prime plus lambda s equals 0. And then if I take just the t functions dependent on t or h of t, then I get t times h prime plus lambda times h equals 0. Maybe we can discuss two cases here. Maybe first case, we can look at lambda is 0. We didn't rule out for this case whether lambda can be 0 or cannot be 0 or positive or negative. Let's assume that it can be a positive number or negative number, or it can be a 0. So if lambda is 0, then you get s prime times x is 0, or s is a constant c1. For t equation, you get t times h prime equals 0, or h equals c2. So u equals c1 times c2, s times h, which is a new constant, maybe c3. So if lambda is 0, then the solution is just a constant. Lambda is not 0. Lambda could be positive or negative. So in that case, first look at the x equation. X s prime plus lambda s equals 0. So we can separate that. X times, or maybe you can write ds by s equals minus lambda by x, and then we can integrate both sides. If we integrate both sides with respect to the corresponding variable, we get ln of s equals minus lambda times ln of x plus a constant, maybe c4. So that's definitely give you something like s equal to x to the power minus lambda, and perhaps a coefficient. You can still write c4, just rewrite the coefficient, rewrite the constant, reuse the constant c4. We don't need c4, so it's a different one. Okay. For now, you can look at, maybe you can just make some room on the side that would be easy to visualize. So the t equation is t times h prime plus lambda h equals 0. That's same equation, except h is in terms of s and x is in terms of t is in terms of x, h is in terms of s, right? The same equation. So the solution will be h equals, maybe we use a different constant c5, t to the power minus lambda. If so, then u x of t is sh, which equals c4 times c5, another constant, say a, times xt to the power minus lambda. And that's all. And we, by knowing some initial condition, we can determine the eigenvalues and the coefficient. But what I have shown in this lecture is two types of problem. The first one was second order elliptic differential equation, and the second one is first order hyperbolic differential equation, and in both cases we were able to apply the separation of variable. Try to look at solving a similar problem from the textbook, and if you have any question, let me know.